Hello, my name is Paula López. I am professor at the University of Santiago de Compostela, and I also have the pleasure of being the coordinator of the Televés Chip Chair on Microelectronics. And within this initiative, we are organizing a summer school in green chips and algorithms for artificial intelligence. Today, I have with me these two researchers I would like to introduce. On the one hand, we have here Jana Nieder. She is an experimental physicist, and she's also the leader of the ultra-fast bio and nanophotonics group. And here we also have Bruno Romeira. Bruno Romeira is a research scientist and PI of the Nieder's ultra-fast and bio nanophotonics. So today we will have the pleasure of having this podcast, and we will be talking about integrated photonics, which is one of the research lines that we are promoting within this Cátedra Televés Chip Chair. So first, welcome. Thank you for joining us for this podcast, and I'm sure that this will be a very interesting talk. So first of all, I would like you to comment for our audience, if you can maybe very simply explain us what is photonics, so integrated photonics, what we understand when we use this topic.
Yes, thank you for the invitation. In simple terms, integrated photonics can be used for sensing and transmitting and detecting light. So it's a circuit that we can use for processing information that comes in the form of light. Mm-hmm. And this comes with interesting properties because light has a unique advantage as compared with other forms of communication. And of course, nowadays we know the most simple transceiver or photonics integrated circuit we have is at our homes when we receive information via light in these small optical fibers and is converted to electricity. And this is the most simple example we have of a photonic chip.
Mm-hmm. Mm-hmm. And what would you say are the main advantages of this technology compared to other existing technologies like standard silicon electronics or integrated circuits?
Mm-hmm. One of the advantages is, of course, the speed at which information can be processed, but also the low losses of energy that in case of electronics often are visible by heating up of the chip elements. Mm-hmm. This is avoided when you use basically light for the information and communication processing.
Mm-hmm. So you have both mentioned light. Mm-hmm. So indeed, light is like the main property of material that we are considering here, right? So the main advantage of this technology, can we say that it is indeed using light, so making...
Indeed. So the name photonics is from the photon as the light, refers to light, and especially light in the visible or near infrared range that we are using for these applications that range, for example, in the interface on the one hand side for computation, but on the other side, for example, also for biosensing. Mm-hmm. And here we work with photonic integrated chips that have, for example, an evanescent field that have light leakage that interacts with biological materials, for example, and we can use this information in a feedback loop to measure parameters of this biological sample, but also potentially to do computation. And that's something that is the base of one of the projects we're working on. It's called Insect NeuroNano. It's using nature and biology as an inspiration for a photonic integrated chip, where we use light as a memory function as well as a computation function. And Bruno is heavily involved in this project, so I think he is the right person to ask some more questions about this.
So would you like to tell us a little bit more about this project and your role in it?
Yeah, we were talking about the advantages of light, right? And light can have properties like polarization of light or different colors of light, right? And insects use these properties of light for navigation. So they have an internal compass that help us to navigate in environments that are completely new. and they use the property of light polarization that we all know. Light from the sun, when it hits the atmosphere, it's scattered, and there are specific angles that which is scattered and depends on the position of the sun. And so insects can use their eye and brain to detect this polarization uniquely, and we try to mimic this behavior by building chips that can sense light, sense polarized light, and also process this in a inspired brain architecture. Yes.
So you are taking, let's say, inspiration from how nature works somehow, right? So it's a sort of bio-inspired computation, let's say.
Exactly. Yes.
Very interesting. I'm wondering, so for example, if we look at other alternatives, such as I mentioned, for example, conventional electronic devices, which are based mainly on silicon, not only, but mainly. So silicon is relatively cheap and available material. So I'm wondering, in the case of photonic circuits, what kind of materials are you using? What is the availability, or are there any constraints in this sense, or about the materials that are normally used within these devices?
We work mostly with 3-5 semiconductors, but also with interconnects that might be made out of polymers. We can think of different material platforms. At the moment, in terms of availability, silicon is much more available than the 3-5 materials, but we are exploring also new sources of, for example, light emissive materials. We are working with 2D materials that have emitters. That is an alternative that is on the one hand side very compact, but also uses very little material overall. So some of the concepts that we develop and test in the 3-5 platforms might be possible to translate into these newer platforms. But at the moment, the neuromorphic photonic computational platforms are in their very early development stage. So we are really at the moment of testing initial concepts and are in this forefront of a future emerging technology, and there it is better to work with let's say these 3-5 semiconductor materials that we have a good control over in terms of, for example, nano processing of the materials. We have to scale down the material to the nano scale. We are establishing processes that help the material to have a more efficient light outcoupling, for example, surface passivation. And also we know the material so well that we can integrate it with other materials, and that's something we started to do, especially in frame of a new European project that is called APEX, the Advanced Pilot Line for Heterogeneous Integration. And one of the key integrations is to bring these semiconductor materials together and have nano light emitters and nano light detectors interconnected. And that is something we were working on using a new technique that is called basically a microprinting with light. We use a femtosecond laser, so another photonic tool, to write interconnections from one nanolight emitter to a nanolight detector to build an highly interconnected chip that can more and more look like maybe a highly interconnected neuronal network.
Very interesting. So you have been talking about the materials which are used and why we use these materials, but you also mentioned something very interesting, which is the processing, right? One of the reasons is that you know how to work with these materials. So since you both come from the INL, so the Iberian Nanoelectronics Laboratory, so I wonder what kind of equipment, machinery, so is it very costly? I guess you need to use very dedicated tools. Can you maybe talk a little bit about this equipment that you need and how you do it at INL?
Yeah. We need very dedicated equipment, but also equipment that is dedicated in a dedicated cleanroom facility. And the cleanroom part, Bruno will discuss more in detail. And then we have other technologies that are more placed in an optics lab, like the femtosecond laser-based 3D microfabrication. It's a long word But what we really do is moving the focus of a laser through a polymer material, and wherever the focus is placed, we can harden the material out. So it is similar to a 3D printer that you might know, where you have a free form that you create by having a nozzle moving over the sample. In our case, we have light of a laser beam that is moving through this material, and we can create any type of 3D shape. For the nano processing, we have a lot of different steps that are conducted in a clean room facility, and Bruno is a specialist in that area.
Yes.
Think that maybe,
No, in fact, in photonics, the process we use are identical to electronics. It's just the materials are different. But the main steps include lithography, etching, and deposition of materials. So we need to do lithography to define the size of the devices we want to fabricate. And then we need to do etching, so remove material in order to have your device in 3D, and then we need to do deposition to have electrical contacts, for example.
So there is this parallelism between the processing or how it is processed to obtain this material.
And in fact, it's because there are also silicon photonics. In this case, even photonics use the silicon foundries to process their silicon photonic devices. So
I think
there's compatibility.
I think that is the dream, right? Arriving to the point in which both technologies can interconnect in a smooth way, right? Of course, as you said, there are the silicon photonics technologies, but as Jana was mentioning, this is still at the beginning. But it's great. There is a path ahead, but I mean, this integration should be smooth, and probably will lead to some very new application domains. And by the way, I would like both of you, maybe you can talk a little bit about what are the main domain applications that you envision for silicon photonic circuits. So it's not silicon photonics specifically, but in general photonic circuits.
Yeah. So on the information and communication technologies, photonics is very strong on interconnections. Nowadays in the cloud, we have clusters of computers that need to transfer data from one computer to the other, or racks of computers to the others. And there photonics is very good because you can transmit data within the large data center with very low loss and very high bandwidth. So I think that is currently already a very strong application that photonics is quite important.
And if I'm not mistaken, I think you're also working on some applications in relation with neuromorphic computation and its integration with artificial intelligence.
Yes, that's a second application that photonics is also in a way competing with electronics, so trying to build hardware dedicated for artificial intelligence. And in this case, you have two approaches. One is using digital kind of processing, the same way electronics works, to process AI algorithms. A second approach that we use is to use brain-inspired essentially key building blocks to mimic the analog spiking signals in our brain, and use that as a spiking neural network that use optical spikes in this network to process information. So this is something we are exploring in the context, for example, in insect-inspired architectures, and also other architectures where you need to sense light and then process in a dedicated circuit. And of course, if you are dealing with analog signals, it is much better to use an hardware that can also handle with analog signals, not digital signals.
Yeah, this is indeed very interesting because it is very well known that one of the main bottlenecks of artificial intelligence nowadays is that it's based on using extremely expensive and hardware-intensive and energy-intensive data centers for training and inference, and they have all these problems of memory access. And indeed, a solution as the one you are proposing goes in the direction of solving all these troubles, which is indeed very important. But I think silicon photonics, besides new computing paradigms, it also has some other very interesting approaches, specifically, I think, in biosensing and other domains. Maybe, Jana, you can talk a little bit about this.
Yeah, in our team, we have very interdisciplinary work, and we developed the photonic integrated circuits on the one hand side for the artificial neuromorphic platforms, computational platforms, but on the other side also in two other main domains. One is biosensing and bioimaging. This is very important for the area of health tech. So, for example, following the impact, the efficiency of drugs on certain disease models, or testing, some therapeutic treatments of a model, or in the area of what we call quantum photonic chips for sensing and metrology, or as well as for computation. So there are two different main lines, or three different main lines in the group. The computation, either with spiking photonic neural networks or with quantum photonics. And for the quantum photonic chip, we mostly are specialized on using materials such as diamond, where single point effects are color centers that can sense properties such as temperature and magnetic fields. And that is very important if you want to map, for example, a cancer where the temperature due to higher metabolic activity is higher than healthy tissue. Then you have a temperature sensor optically that non-invasively can measure basically relevant parameters in the tissue. If we can combine all these efforts in a joint platform that can sense and calculate at the same time, that is the future vision of this research, to combine the technologies in this sense.
Yeah, this is exactly what I was going to mention. So there is a wide scope of possibilities, even possibly technologies still to explore. And what was your vision about this in the future? So you already mentioned this line. So Bruno, what is your opinion? So what do you think the future will bring in photonic circuits?
Yeah, there's many important things we can consider in the future. As Jana was mentioned, we are trying to combine these different technologies. And for sure, there are cases where if you combine biology and artificial chips, this can bring advantages, because you can bring synergies what the biological system is doing and what the artificial system is doing, and combine this in a different platform that is more a hybrid platform. And maybe photonics can help on this, on bringing this together.
Yeah. So what is clear is that there is a very exciting future and open, full of possibilities in this new field. So, I would like to finish by thanking you both for being here, for participating in our summer school, and congratulate you for the excellent work that you are developing at INL within this photonic area. So thank you very much for being here. It has been a pleasure.
Thank you for the invitation.
Thank you. Thank you for the invitation.